So in this video, we're going to move on to kind of a new topic in the acid-base world, and that's this whole field of what we would call an organic acid. Now, organic acid, of course, refers to organic compounds, and organic compounds we've already described are mainly carbon-based compounds. And those carbon-based compounds could have a few oxygens or nitrogens or sulfurs or something on them, but it's got to be carbon-based. It also has to be covalent in order for it to get to carbon-based to be classified as an organic compound. So one of those first organic type of acids that you've always learned about has been acetic acid, or aka vinegar. Just a weakened solution of acetic acid is what vinegar is. And this is CH3COOH. So as you can tell, it is carbon-based. There's a few hydrogens that's there. There's a few oxygens that's there. All across the board, this is all covalent or non-metals. So it meets the definition of an organic compound. And these are the types of acids that we're going to be focused on for the next few minutes. Now, of course, acetic acid is not the only one. There are tons of others. And almost all of the organic acids that we will talk about in organic chemistry are going to be weak, which means that they will have pKa values that are associated with them. Keep in mind that we talked about strong acids, and there were really only 6 or 7 total, and that was it. So the majority of the organic acids in a lab, I'm not saying all of them, but the majority of the organic acids in a laboratory are going to be weak, and because of that, they will have pKa values that are associated with them. So organic acids is the same definition as an acid. They are going to donate or give off a proton. Okay, their structure is just organic based. That's really the only difference here. So that definition's not changing on us, and you need to understand that. So everything that we've talked about up to this point stays true here. There's no differences. But we like to categorize things, especially in organic chemistry. We like things to fit in a nice little box. Even though there's no such thing as a nice little box that everything will fit in, we try to at least classify things whenever we can. It makes our job a little bit easier. So there's different classifications of what we are going to look at as our first organic acid group. And here are the 4 classifications that you need to become acquainted with. So the first one is a carboxylic acid. The second one is an alcohol. The third one is called an amine. And the next one is a protonated compound. So these are the 4 classifications that we are going to be referring to throughout the rest of this video and maybe upcoming videos as well. So if you look at the first classification, carboxylic acid, what does that actually mean? Well, a carboxylic acid in organic chemistry is a C double bond O with an OH group, and then whatever over here for that 4th bond. It's normally other carbons and hydrogens. We call it a random alkyl group. That's what we refer to that as. Sometimes we actually write the letter R over here to the side to represent anything random that it wants to be. But normally it's other carbons and hydrogens. So this area right here is what's going to label this as a carboxylic acid. So this is the first classification that I want to talk about, and here are 2 examples of carboxylic acids that you would see in a lab, or you would see in organic. So over to the left, we have acetic acid, which is basically vinegar that's been weakened, or which is basically vinegar. It's a 5% solution of acetic acid. So that acetic acid is something that you're very familiar with. It's probably in your pantry at this point in time, and that is classified as a carboxylic acid. Again, the reason is because of this C double bond OOH group. So acetic acid has a pKa, and this pKa is a 4.76. So we've used this before in the past. That's why that number seems familiar. It's been in some of our previous example problems and equations that we've looked at, but this is an example of carboxylic acid. Over to the right-hand side, you're going to see another type of carboxylic acid. Notice the difference here is that this has a CH3 group and this just has the hydrogen group. Remember I said it can be anything random. So here we go. There's a prime example. But it still has this C double bond OOH on it. So it's still classified as a carboxylic. That carboxylic acid in this case is called formic acid, and this is the acid that is typically in ant stings or ant bites. If an ant bites you, then it begins to burn or it feels uncomfortable, then this is because it has just injected formic acid inside of you, and that acid is beginning to eat away at your cells and your skin and everything else. So this is formic acid at its finest. Well, it's also a weak acid. That pKa value is a 3.75. And if you compare these two, formic acid is going to be a little bit stronger than acetic acid because its pKa is lower than acetic acid. Remember, think of it kind of like pH scale. The lower the pH, the more acidic. Therefore, the lower the pKa, the stronger it is. So here are two examples of carboxylic acids for you. There's tons of others, and we can write them down all day long. But these are just two examples that I kind of want to introduce to you at this point right now. Do you have to memorize the structures? Not necessarily, not yet. Do you have to know what carboxylic acid functional group is? And the answer is yes. So you have to make sure that you know carboxylic acid refers to C double bond OOH. That is a have to. So, again, I told you that you shouldn't have to memorize things, but we have to learn things. And we have to learn that COOH is a carboxylic acid functional group. All right, next is the alcohol classification. The alcohol classification is any time we see OH onto a molecule. Okay, now I know you're probably looking at this and saying, well, why isn't that an alcohol? That's because that OH was attached to a carbon with a double bond O. So this is treated completely separate. So if this OH was not attached to a carbon with a double bond O, but to something else, then that OH group could be called an alcohol group. So two examples of alcohol are here. Okay, the one to the left and the one to the right. These are both alcohols. Methyl alcohol is a very common solvent in organic chemistry. We use it for a number of different purposes. It loves to absorb through the skin, and it can also cause blindness if you allow enough of it to absorb through your skin. Well, this is the OH group that's right here. Okay, so that OH group makes the structure an alcohol. And that pKa value is 15.5. If I look over on the right-hand side, this is ethyl alcohol. Again, the OH group makes this thing an alcohol. All right, so if that's ethyl alcohol, which, by the way, is drinking alcohol in the ABC store, that pKa is going to be 15.9. They're pretty close to each other, aren't they? 15.5, 15.9, but in general, these numbers are much higher than the numbers for carboxylic acids. And these are pretty close to each other. I mean, we're talking about high 3s and high 4s in that range based on the two examples that I'm showing you here. So carboxylic acids have much lower pKa values than alcohols do. What that means is that carboxylic acids are going to be stronger acids than alcohols are going to be. So this is kind of the relationship I want you to start thinking about as we progress through these classifications. So these can donate a proton. These can act as an acid. But the problem here is that they're a little bit more stubborn. These pKa values are much higher, which means that our pH levels have to be over a 15.5 or 16 in order to get this compound to spit off a hydrogen. And quite honestly, we never really are working that high most of the time. I mean, we can, but this is going to be very rare. So, alcohols can be protonated or can deprotonate. They can spit off a hydrogen, but you have to make sure that the pH levels are allowing that to happen. And it's just very uncommon. But we can still assign acidities to them. We can still assign pKa values to them. Another tidbit of information, Ethyl alcohol was drinking alcohol. Ethyl alcohol was also what the old moonshiners used to make back up into the hills of North Carolina, West Virginia, and Kentucky, and Tennessee. So all of this ethyl alcohol was getting distilled. Moonshine was getting created. They were distilling that moonshine off. And depending on the process of the distillation, how pure is the ethyl alcohol, there could be remnants of methyl alcohol that were in that moonshine. And it wasn't uncommon for people to drink some moonshine in the early stages and actually get alcohol poisoning from the methanol that was located in that moonshine sample. So these people could go blind, of course, if they drank enough of it, and these people could have had a trip to the hospital because of that as well. So methyl alcohol is a contaminant of ethyl alcohol and alcohol production, especially with moonshine. So if you're a moonshiner and you're making your own alcohol in your garage, don't tell me about it, but this was a common problem that was happening back in the early days and maybe still is happening today. Who's seen the show Moonshiners? All right, so the next category is amine. And amine was that third classification that we wrote down. And an amine is going to be a nitrogen-based compound. Typically, it's NH2. This is what we see most of the time. And the reason that you don't really see NH2 over here, I want you to think of it as kind of like HNH2 in a way, but this is why I'm saying it's nitrogen-based. There's actually a couple of alternatives that are out there for amines. So it can be NH2, it can be this HNH2 rewritten as NH3 in this way. It could be an NH with some kind of other alkyl group on it and some kind of other alkyl group on it. If it has a nitrogen in it at this point in time, folks, we're going to look at it as an amine structure. So this amine is an NH2 attached to a CH3 group, and this is an NH2 really attached to an H that they just rewrite as NH3. So pKa here is 40, and pKa here is 36. Again, the amines are very close together, but if you compare that to the other classifications that we've looked at so far, these pKa's are way higher than the pKa's for alcohol, which are way higher than the pKa's for carboxylic acids. What that means is that amines can be acidic, but folks, you've got to get a pH that is greater than 40 in order for these things to be acidic, and that is very difficult to do. So there is acidity. They can spit off a proton if given the right circumstance under normal situations, but it's going to be very difficult. So these are acidic, but by no means are they acting as acids, if that makes any sense at all. Okay? They can become acids, but you have to really jack the pH up of that solution that they are going to be in. So this is a problem, okay? So pKa's of 40s, these are very, very weak, okay? And they do not have any strength as far as acids go. Alcohols are a little bit stronger. We can at least get them to protonate under the right circumstances pretty easily in a lab if I play my solvent off the right way. And carboxylic acids are even stronger. And it doesn't take a lot of effort at all for those to spit off a proton and become acids for me. The last category we said was protonated. Well, we're going to look at protonated amines. These were these nitrogen-containing compounds. And if we slap on an extra hydrogen here and make these things positive as far as their formal charge, then we can really change the pKa's of those amines. And now these pKa's are lower than the alcohols, which means that protonated amines are actually stronger acids than alcohols are. You can see the big change of pKa values just by placing an extra hydrogen on this molecule. What that means is that this molecule realizes that that positive charge is there and it is not balanced. It's not neutral. So it would like to spit off a proton when it can. If it gives the opportunity to spit it off, it will spit it off. Only thing I have to do to ensure that is my pH has to be greater than maybe 11. And if I'm working in that kind of environment, then I am ensuring that this amine is spitting off the proton like it needs to be. And if it's spitting off proton, it now becomes an acid. So as a summary table, this is kind of what we are leading up to. So we've talked about carboxylic acids here. And these carboxylic acids tend to have a pKa of around a 5. If you had to do an average of them, this is typically the average of those carboxylic acids. I mean, acetic acid was 4.76. Formic acid was 3.75. By the time you add all of these together, do an average, 5 roundabout is going to be that value. The alcohols are going to be on a 15. So that methanol was 15.5. The ethanol was 15.9, almost 16. So if we do an average of all the alcohols, the common ones, then we're going to see that these pKa's center around 15 almost all the time. Okay? So that's the classification that alcohols are going to go into. Protonated amines. Protonated amines are around a 10 on average. And we've just discussed why. They have this positive charge, they don't like it. Under the right circumstance, they're going to spit off that proton, and they are actually stronger acids than even alcohols are. Notice on the chart, they don't even bother listing amines. I told you that these amines had pKa's of 40s on average. So if you had an amine and you had a pKa of 40, it is very, very difficult in order to get that thing to behave as an acid, and they actually don't even bother writing that on this chart. That's how bad those things are as far as acidity goes. Over on the left-hand side, amines are not the only thing that can be protonated. Anytime you protonate something, you always increase the acidity of it or the strength of it. So if I take an alcohol and I protonate it, well, you're going to see that here in the first column. If I take a carboxylic acid and I protonate it, then you're going to see that in the very first column as well. If I take water and I protonate it, you're also going to see that in the very first column. And all of these protonated compounds are going to have a pKa less than 0. So superacids, I mean, those things are going to be spitting off protons whenever they can because they do not like that setup. They do not like that structure. They do not like that extra positive charge, and they're going to get rid of it whenever it's possible. The other thing, one last thing I want to talk about, is just to refocus on water here. We just mentioned it. Water can behave as an acid, and it can spit off a proton. And that water falls in the same category that an alcohol does. The question is why? Why do they put it with an alcohol? Well, another way to rewrite water is HOH. And there you go, folks. You now see why they do it there, because that is a OH group. And you might look at this and say, well, that OH group is there. Why isn't this classified as an alcohol? Well, kinda. I mean, it's very, very close. So that's why you see water and alcohol in the same column, because they somewhat have the same what we call functional group that's associated with them. And that's a OH group area on the structure. So that's where I'm going to stop this video. It's giving you a little bit of insight about how we can now look at structures and maybe don't even need a chart. We can look at these structures, and if they have these functional groups on them, if we can classify them as an amine or carboxylic acid or an alcohol or something that's protonated, we can already determine which one's going to be stronger than the other one. We do not need a chart to do this. We do not need pKa's to do this. We just simply look at these structures, and we can gain this type of information very quickly just because of how this molecule is set up. So in the next video, we'll continue on with this discussion, and we'll go on and we'll look at some more example problems. So stay tuned, come back, get you a drink of water. I know I'm making your brain work out a little bit, but come back. It's good for you. It's very healthy. Bye.